we start to talk about how to do things with Onyx. The first thing to do here, though, is to talk about what score matrix, that is, what particular form of our data we want to use for a structural equation model. All of statistical modeling is an act of journalism. That means that we're actually talking about the aspects of the data that we want our statistical model to explain, and we're going to leave some of the other details about our data a bit to the side for the moment. If you're looking at regression models, very frequently we talk about standardized and unstandardized regression rates, for example. Sometimes we talk about the intercept for a regression. Sometimes we leave that off because we're really interested in talking about the unstandardized or standardized value. So the first thing I want to do is to introduce three different ways to think about your data. There's the raw form of the data, which uses what is called an adjoined matrix, and we'll talk about that later. There's the deviation score version of our data, in which the mean of each variable has been subtracted from every observation, and there's the standardized version of our data. One of the things that's easiest to talk about here is to think about this in terms of an Excel spreadsheet. So let's come back and share a spreadsheet here. What I have here is the Galton data set expressed in our raw score, deviation score, and z-score fashion. And just as a little bit of a refresher, or maybe three forms, and think about what those numbers are actually telling us. What I have here is the Galton data set expressed in our raw score, deviation score, and z-score fashion. And just as a little bit of a refresher, or maybe an introduction if you've never talked about this before, we might talk about our summary statistics in each of these three forms and think about what those numbers are actually telling us. Let's talk about the raw data that we have here. 61.7 inches for a child, and the mid-parent height is 70.5, for example. If you're looking at just one row of this, what are you actually going to do if you want to interpret those things? Is this child a short child or a tall child? What about this parent? We don't really know that, but we do know on average, the average height of the children is 68, and the average height of the parent is also around 68. So this is the case of a child who is below average, the mean is 68, that child is 61, and a parent who's a bit above average, that parent score is 70, and the average parent height is 68. Well, we can't really go through and interpret each line of these data without coming back and looking at the mean to know if this is above or below the average. So these summary statistics inside of Excel tell us the means of these two variables and the amount of variation. We can see here that the amount of variation in children's heights is a little bit larger than the amount of variation in the mid-parent is of the data. The deviation score version of our data takes the actual value and subtracts the mean out. So we can see up here, if you're looking at the formula, this is 61.7 minus 6809. And I repeat that process for all of the observations in my data set. I do the same thing for the parent. So I take this 70.5 minus 68.31, that gives me 2.19. And I do that for everybody. If I do this across all the observations in my data set, because I have subtracted out the mean of my two variables is 0. But the standard deviation and the variance, for that matter, are the same as they are in the original data set. For this reason, the deviation score matrix is a way to express your data when you're not really interested in the score per se. You're interested in knowing if patterns above the mean on one variable tend to be accompanied by patterns above the mean on the other, below with below. The standardized version of the data consists of taking this deviation score version and dividing by the standard deviation. So this minus 2.54 is this variable divided by 2.52. And I again do that for all of the variables. These things are sometimes known as z-scores. You may have heard them before. And just as we lost information about the mean when we take a deviation score version of the data, Once we calculate a z-score, we have lost information about different variance across our variables. So to summarize, raw score versions using something called the adjoined matrix, which we'll get to later, are useful if you want to explain overall level in your model and patterns of variation. Deviation score variables are useful when you're interested in knowing about covariation between variables and you want to explain how much variability there is. Z-score data is useful when you're interested in looking at correlation coefficients between variables, or if you're interested in knowing the proportion of variance in a particular variable explained by other variables in the model. So let's stop here and come back and do this inside of Ωnyx. As we talked about before, the Galton data set is now read in for us. And now if we wish to do some statistical modeling, we're going to have to open up a model page. So to do that, come up to the little teeny tiny Ωnyx logo there and say, create an empty model. And you will then see that you have a little drawing board that you can put your model on. So in order to put your variables into this model, I can click on one variable, hold the Shift key, left click on the other, and then left click and drag this over. And I will now have the variables in my model available for my statistical analysis. Let me left click on this variable and move it over a bit, and left click on child and move that over a little bit. In order for me to look at calculating a correlation coefficient, I'm going to have to transform these two variables into z-scores. To do that, I'm going to right-click on a variable and left-click on Apply Z-Transform. Notice that the variance of parent has now gone to 1. We'll do the same thing for this other variable. Apply Z-Transform there. And now child also has a variance of 1 because the parent and child variables have been transformed to a mean of 0 and variance. If I want to calculate a correlation coefficient between these two variables, I'm going to draw a sling joining parent with child. To do that, I'll hit the Shift button, right-click, and drag over to child. And you'll now see that I have a double-headed arrow here that expresses the correlation between these two variables. By default, Ωnyx is going to call that a fixed variable. So in order to free that parameter, I will select this. It is now a free parameter in my model. And you can see from this that the estimated correlation between these two variables is 0.46. Let's go back and check that against what we would get in a software package that we would normally use. Here, for example, is SAS. And I can calculate the correlation by running a prop core. And we'll see that we get exactly the same number out. Maybe you're somebody who likes JASP. Well, we bring up JASP, read our data in, and select regression. And linear regression under that, and say we're going to have parent as our predictor variable and child as our dependent variable. We'll see that we get the following regression. I get the correlation here of 0.45 between variable 1 and variable 2 as well. So let's come back to Ωnyx. Say I were interested in calculating a standardized regression weight. So let me come up here now, and instead of having a double-headed arrow, I'm going to remove this path, selecting it and hitting the delete key. And now, instead of hitting the Shift key and right-clicking, I'm just going to right-click, and that will give me an arrow. And as before, I'm going to have to free that parameter. Move that over just a little bit so we can see it. And we now see that we have a standardized regression weight of 0.46. Remember that if you have only one predictor, the standardized regression weight is going to be equal to the correlation. And that matches what we see inside of other packages as well. say I was interested in looking at regression inside of SAS, I would type in the following code, proc_reg with model, and if I wanted to see standardized coefficients, I would be sure to include this option that requests those as well. The output that I'm going to get will look like this. Over here you see the unstandardized regression weight, that intercept, and over here you see our familiar value for the standardized estimate. Okay, so let's go back to Ωnyx again. Say now that I'm interested not in calculating a standardized regression weight, but I want to take a look at the unstandardized regression weight. To do that, I'm going to come in and remove the z-transform by right-clicking and then left-clicking to remove that z-transform. Then you'll notice now that my model has changed a bit. These values represent the variance of the predictor variable, and over here we see the error variance associated with the error term. This 0.65 is the unstandardized regression weight, and that matches with what we would see inside of SAS. For example, here's our 0.46. Okay, in this diagram now we're going to see the variance of the predictor variable, the unstandardized regression weight, and the variance of the error term. This 5 has a relationship with something that you already saw when you took a regression class. In your regression class, you may recall that you saw something called the root mean square error, 2.23855. This number is the square root. It's an estimate of the standard deviation of the error. And apart from some minor differences in how degrees of freedom are calculated between a path diagram and a regression model, this is going to be more or less the square root of that error term, which we can see. So the models that we have here, the standardized version and the deviation square version, do not have the mean in the model. Sometimes when I'm interested in, say, actuarial prediction, I might want to know who is actually going to get a grade point average of 3.8 if I'm studying college outcomes, or if I want to actually know what the predicted value in my regression model is for a child height and for a parent height, I'm going to have to put the mean in the model. So to put the mean in the model here, I'm going to come down here and right-click on Ωnyx and select mean structure and make sure that explicit means is now shown. And to estimate the intercept, I'm going to have to add another variable, the constant. This constant has as its interpretation, which we will see later in the chapter, has the function of being a column of ones. I right-click and I join the constant to the criterion variable, and I join it to all of the predictor variables that I have in my model, and then I come back and I free those parameters. Left-click, I can kind of move these around a little bit. And you will now see that I have the unstandardized regression weight and the intercept that matches what I see in a regression model. So if I come back to SAS and take a look at that, here's my intercept, and here's my unstandardized regression weight. If I'm playing with JASP, here's my intercept, and here's my unstandardized regression weight. Okay. A path model is also useful because it's going to tell you what the mean is of your predictor variables. So in this particular model, this path diagram is saying that the mean of this predictor variable is 68.31, which matches what I have when I mouse over that value, and you'll see that the mean is 68.31 for child. Okay, so this is my gentle introduction to drawing a path diagram in Ωnyx, and to use something that hopefully you've already encountered, what a simple linear regression looks like, and the 3 different path diagrams that you can look at. Before I go, I wanted to highlight the fact that Ωnyx will also generate some program code that you can use in other structural equation modeling programs. If I right-click on this and select Show Script, I can then generate, say, some lavaan program code to do exactly the model that you're seeing here in Ωnyx. Similarly, if I want to take a look at Mplus, this is what the Mplus program looks like for doing exactly this model on that platform. And similarly, if you are interested in OpenMx, here's the code. Well, it's a little bit of typing, but one of the nice things about Ωnyx is it gets you some code that you can quickly and easily come in and use. That's all I have for you in this model. We'll make another video where we talk a little bit about how to go from this program code into JASP, or to go from this code into lavaan in R, or this code into Mplus. Thanks for watching.